is called as the periodicity property. So now let us look into the symmetry property. So the symmetry property, it's a very important one. So which is can be useful in order to reduce the number of calculations in the fast Fourier transform. It says like this. So it is omega into the power of a plus n by 2. So this is equal to the minus omega n to the power of a. So the n by is the thing, but n is the periodicity of the Twiddle factor. If the value it is exceeds above n by 2, so then this can be written as minus omega into the power of a. Let us consider the proof of this one. So in order to prove this one, let us consider the LHS part we'll consider. So it says omega n to the power of a plus n by 2. So in order to prove this one, I'm going to convert in terms of the exponential series, exponential functions. So it is expressed as e to the power of minus j. So it is a 2 pi divided by n. So that is for the Twiddle factor, and the remaining quantity is a plus n by 2. So this one we can rewrite as e to the power of minus j 2 pi divided by n into a. So I'm going to apply law of indices for the exponential terms. So the remaining quantity is e to the power of minus j 2 pi divided by n into. So the remaining quantity is n by 2. So here this n and n will get cancelled. So 2 and 2 will get cancelled. The remaining quantity is e to the power of minus j 2 pi. Let us find out the value for the e to the power of minus j 2 pi by converting in terms of the sine function and converting in terms of the cos function here. So e to the power of minus j pi. So we can rewrite that one as so it is cos pi minus j sin pi, and the value of the cos pi it is equal to the minus 1, and the value of the sin pi this is equal to the 0. So minus j into 0. So this value is equal to the minus 1. So we can say that so the e to the power of minus j pi. So this value is equal to the 1 will get here. So what we got the remaining quantity is nothing but, so it will become equal to the LHS part is e to the power of minus j 2 pi divided by n into a, 2 pi divided by n into a. So into minus 1 will get here. So if we convert back this into the Twiddle factor, it will become, so minus 1 will remains constant here. So it is omega n to the power of a will get here, omega n to the power of a. So we can rewrite as, so this is equal to the RHS part what we got here. So we got here that is omega n to the power of a plus n by 2. So it is equal to the omega n to the power of a multiplied by the minus 1. So this is the important property of the Twiddle factor, which is called as symmetry property. The usage of this property is, suppose if I know the half of the values for the Twiddle factor, the remaining half can be found out by using this one here. For example, if I consider the values something like this, I'll take the example of the n will be taken. So let us take n is equal to, so I'll take the example n is equal to 8 will be taken, so that a can take the value from so that is it will take the value from 0 1 up to the n minus 1. So in case of n is equal to 8, a will take the value from 0 1 up to the 7 it will take. Now let us see how this property can be useful. For example, if I want to find the value for the omega 8 to the power of 6, I want to find out here. So by using this property, this property we can express like this. So here the value of n by 2. So n by 2 is nothing but it is 8 by 2. So it is equal to 4 here. So I can express the omega 8 to the power of 6 can be expressed as a plus n by 2. A plus n by 2 we can express here in the terms of this one. So it will be omega 8 to the power of 2 plus 4 we can express here. So this is nothing but n by 2. So this will become equal to the omega 8 to the power of minus 2. So omega 8 to the power of 6 is also equal to the minus 8 into omega 8 to the power of 2. So similarly, we can find out the omega 8 to the power of 7 we can express as omega 8 to the power of 3 plus 4, where 4 is nothing but n by 2 value. So this is omega 8 to the power of 3 multiplied by the minus 1. So like this we can express, if I know the half of the values for the Twiddle factor, we can able to find out the remaining half values we can find out by using the symmetry property. So this is the very useful properties. So far we have seen the two properties. One is called as the periodicity property. That is, as per the periodicity property, it is omega into the power of a plus n is equal to the omega into the power of a, and other one is the symmetry property. Omega into the power of a plus n by 2 is equal to the, so minus omega n to the power of a. So these are the very two important properties of the Twiddle factor which will be having more usage. and we are going to apply these properties. We are going to explore in case of the fast Fourier transform in order to reduce the number of calculations. So now, since already we have seen the periodicity property of the signal Twiddle factor, now because of this one, the x of n and x of k is going to exhibit the periodicity. That one you're going to call it as a implicit periodic functions you're going to call here. So I'm going to consider the next one, which is called as the implicit periodic functions. I'm going to consider implicit periodicity we can consider here. Implicit periodicity we can consider. What he says is, so since in the DFT formula we have x of k is equal to summation n is equal to 0 to the n minus 1 x of n into omega n to the power of k n. So because of that factor omega n to the power of k, the sequence x of k is going to exhibit the property that is called the periodicity property here. Let us prove that one. That property, so plus x of k called the k. So now to prove this one, I'll consider the DFT formula. We'll consider. So we have this formula. This is a formula for the DFT. So since I want x of k plus n, what we can do is we can replace the k by the n plus k in the equation 1 here. So in the equation 1, so what we can do is, so we can replace the k by the n plus k. We can do replace here. So this will become equal to the x of k plus n. So it will become equal to summation. Wherever the k is there, I can replace with the n plus k is x of n into omega into the power of, in place of k here, in place of k, I can do replace with the k plus n here. So this will become k plus n. This will become k plus n. Since omega into the power of k plus n is there, I can apply the periodicity property. So I can apply the law of indices for the exponential terms. So this will become equal to the summation n is equal to 0 to the n minus 1. So it's x of n omega into the power of k into small n into omega into the power of k into n. So we know that omega into the power of k into n is nothing but this value is equal to the 1 here. So already we have seen this one. So the remaining quantity and the LHS part will be, RHS part will be summation n is equal to 0 to n minus 1 x of n into omega into the power of kn. So this is equal to the x of k. So we can say that x of k plus n so is equal to the x of k. So the sequence we can say that it's a periodic sequence here. Periodic property, or it is a periodic sequence. It is going to be satisfied. So because of the Twiddle factor, the sequence even x of k is also going to exhibit the periodicity. So that one you are going to call it as a implicit periodic function we are going to call. Now similarly, let us prove the periodicity of the sequence x of n also. Let us prove that. So we will consider the periodicity of x of n. So let us look into that one. So that is from the IDFT formula, what we have is, so from IDFT formula, so what we have is the x of n is equal to the 1 by n summation k is equal to 0 to n minus 1 x of k into omega n to the power of minus kn we have, minus kn we have. So this is the IDFT formula. Here also it is going to exhibit the periodicity. So for n to be, so for x of n to be periodic, what the condition is, x of n plus n should be equal to the x of n. So let us prove that one. So let us call this equation number 2 here. Let us call this as equation number 2. So since in the equation 2, what we can do is, in the equation 2, let us replace n by the n plus capital N, replace n by the n plus capital N. So it will become x of n plus n. So this will become equal to the, wherever the small n is there, we can do replace with the n plus capital N. So we'll have summation k is equal to 0 to n minus x of k will remains like that only. So omega into the power of minus k into n plus capital N into k. So again, let us apply the exponential indices. Let us apply here. So it will become summation k is equal to 0 to the n minus 1. It is x of k into omega into the power of minus k into n into the Twiddle factor omega into the power of k into capital N. So again, this is the minus is there. Again, this value is equal to the 1. this value is again equal to 1. The remaining quantity will be, so x of n plus n. So this has become equal to the 1 by n summation k is equal to 0 to the n minus 1 x of k into omega into the power of minus kn. So this is equal to the x of n we'll get here. So this is which is going to be prove the periodicity of the x of n. It is going to prove. So that is as per this one, x of n plus capital N is equal to the x of n. So therefore the sequence x of n is the periodic sequence. So such kind of sequences, we are going to call it as the implicit periodic functions. So because of the Twiddle factor, the sequence even x of n and x of n plus n is also going to exhibit the periodicity. Such kind of sequences, we are going to call it as the implicit periodic functions. So now we come to know that the sequence x of n is periodic, and even the DFT x of k plus n is also the periodic here. That is, it is equal to the x of k plus n, and even the Twiddle factor is also the periodic function here. So these are the periodicity of the sequences. Now in the next session, let us see Twiddle values we can find out. Let us see in the next session.